Hi, this short presentation will talk about convex sets and their relationship to weighted averages. This will be useful later on when we talk about Bezier curves, for instance. But let's start off with a definition. We're working with Rn, n-dimensional space. We let A be a subset of Rn. So A is a set of points. A is called convex, provided the following holds. For all x and y members of A, the line segment joining x and y is a subset of A. Another way to say the same thing is that for all x and y in A and all scalars alpha in the interval 0, 1, lerp x, y, alpha is in A. So our picture is there's some set A, and if we take points x and y, and we join them by the line segment. Maybe we go fraction alpha of the way. Then lerp x, y, alpha is in the set, and since alpha could be any value between 0 and 1, the whole line segment is in A. Now this example that I just drew on the board is not convex, because I could take x here and y here, and join the line segment. And those points in the middle are not a subset of A. A is this sort of lozenge thing here. Likewise, there's another spot where A dents in, and it's not convex. So for some examples of convex sets, this includes, for instance, something like this, an egg-shaped kind of thing. You take any 2 points between them, 2 points x and y, and look at the line segment between it that lies inside there. Or some sort of polygonal object where there's no place that A dents in. So this is also convex because, again, you take any 2 points x and y, the line segment, joining them is a subset. On the other hand, some examples of non-convex sets. Well, we already saw one here where it had this little bowing in. More generally, anytime you have some sort of denting in, if this is the set A here, it's the interior of this thing, well, we can look at, say, a point x here, and a point y here, and then the line segment joining them is not a subset of A. Or we might have some sort of annular type of region. Think of some ring like this, where A is this portion that I'm shading in. But this middle part is not a subset of A, these are not members of A. And then, of course, we can take x here and y here, and this line segment is not a subset of A. So non-convexity comes up most typically where we have sort of indentations on the border, like we've seen here, or where we have holes in the middle of some type. Convex means the type of picture we have here. As a definition, the convex hull convex hull of A, and A is still a subset of Rn, is the smallest subset of Rn which is convex and contains A as a subset. So this is a definition. You might ask, does every set have a convex hull? And the answer is yes, every set does have a convex hull. The proof of this, which I will just say very briefly, is you may have seen this kind of proof before in an algebra class. We know there are some convex sets containing A. For instance, the whole space Rn is convex. And it's also not hard to see that the intersection of arbitrarily many convex sets is convex. So if we just take the intersection of all the convex sets which have A as a subset, then we get a convex set which has A as a subset. And since we took the intersection of all of them, it is the smallest convex set containing A as a subset. So that would be the proof that the convex hull exists. So the fact here, as I just outlined, for any A subset of Rn, A has a unique convex hull. And it's again unique by the method of proof I just gave. If you had two convex hulls, their intersections would also be a convex set containing A. We can also characterize this as follows. The convex hull of A is the set of weighted averages of members of A, namely this following set. It's the set of W such that for some x1 through xk in A, W is a weighted average of x1 through xk. Another way to say this is it's the set of W such that for some x1 through xk in A and some alpha 1 through alpha k, all greater than or equal to 0, with some alpha 1 plus dot dot plus alpha k equals 1, W is equal to alpha 1 x1 plus alpha 2 x2 plus dot 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 alpha k xk. There's a proof in the book, so I'm not going to give you the proof in the video here. It's actually pretty straightforward to prove, but you have to think through the definitions carefully to get the proof correctly. So, as I already briefly alluded to, this will turn out to be useful in a variety of settings, but most notably for us, when we define Bezier curves in a few weeks, we'll form points on a Bezier curve as weighted averages of the so-called control points. And this theorem will tell us that the weighted averages of the control points lies in the convex hull of the control points, and will give us control on where the values are on the Bezier curve. But that's the end of this presentation. Thank you very much.